the Churchill Professor of Mathematics and Information. Welcome,
Thank you very
Ioannis.
much. Thank you, Andrew. I'm extremely pleased and feel privileged to be here to honor Andrew on this wonderful occasion. Thank you very much for the invitation and to the organizers for doing all this. What I'd like to talk about today is three or four, depending on how you count, different versions of information-theoretic statements for finite definite theorems, and I'll describe exactly what all of these mean. And this is joint work with Lampros Gavallakis, Mario Berta, and Ollie Johnson. Lampros and Ollie are here, so they can correct me if need be. So first, I want to give some context and take this opportunity to also highlight some of Andrew's spectacular inspiration in this area of approaching classical or even not at all so classical probabilistic results from an information-theoretic point of view and connect them a little bit with exchangeability, then a little bit more history on the famous representation theorem of Definetti that I'm sure all of you are familiar with. I'll just remind you a little bit where it comes from and why we're interested. And then I'll show three versions of an information-theoretic Finetti-style theorem for finite exchangeable vectors. And in the end, I'll describe a much more recent result with Ollie and Lampros. We're using not so information-theoretic ideas. We were able to get an information-theoretic looking result that's, in a certain sense, optimal. Okay, so I hate cliches as much as the next person, but one's tempted to speak of the unreasonable effectiveness of information-theoretic thinking in understanding and deriving probabilistic results. There's been a long series of works going back to the mid-50s. I'll describe some of them. And it turns out that thinking information-theoretically has great benefits in many cases. And one benefit is that it gives you new ways to look at results and interpret and understand them deeply in a different way. Then sometimes this understanding actually leads the way to technical progress, and some of the results that we've seen established in these using these methods are, in fact, the best known results, state-of-the-art results in probability. And they also sometimes give new proofs illuminating different aspects of known results. So the story begins in 1958. This is not a very important result in itself, but it was the first one of its kind. Hayek used an information-theoretic trick to prove a result about Gaussian measures. Then, in 1959, Linux gave an information-theoretic proof of weak convergence in the classical central limit theorem of IID random variables. And this started a very long series of works that are still going on today. I'll say a little bit more about them in a moment. The following year, Rényi showed, again using very elegant information-theoretic tools, that Markov chains, finite state Markov chains with all positive transitions converge to equilibrium in relative entropy, again, using information-theoretic tools. And in the 80s, Cheezer produced a series of spectacular works that drew beautiful and deep and powerful connections between information projections and their application and use in probability and statistical mechanics and in statistics as well. In particular, in the context of probability, which is what I'm just outlining here, he proved what are probably the strongest versions that we know of Sanoff's theorem for IID random variables in general state spaces, and what's sometimes in information theory circles called the conditional limit theorem or the Gibbs conditioning principle in statistical mechanics. Right. Then Andrew entered the picture, and he first proved this version of the central limit theorem. This was a paper written or published in 1986, which was very influential. He proved that the relative entropy between the law of the standardized sum of IID random variables, zero mean and unit variance, so that we know these go to Gaussian, the relative entropy between their law and the standard Gaussian goes to zero in relative entropy, if and only if this relative entropy is ever finite. In itself, this is a very satisfying and elegant statement, and it was particularly exciting because the method of proof was different. It didn't use characteristic functions. It didn't use Lindbergh's method. It used more information-theoretic tools going through Fisher information and establishing this result that drew a lot of attention and sort of restarted the engine of looking at probabilistic results information-theoretically. A less well-known result, but equally exciting and important, is Andrew's proof of the martingale convergence theorem using information-theoretic methods in some work where he actually, and I'd encourage you, especially the more junior people among you who are looking for fun stuff to read, there's a series of very interesting results having to do with the behavior of relative entropy of monotone sequences of sigma algebras. These are very natural objects to look at, it turns out, information-theoretically, both technically and intuitively, because, monotone sequences of sigma algebras naturally come up when one wants to talk about increasing or decreasing information. Right, then in 2000, he proved this very elegant result, which says that any reversible Markov chain that has a unique stationary distribution converges to that stationary distribution monotonically relative entropy, if and only if this relative entropy is ever finite. Again, the proof is very, very neat. Like all of Andrew's stuff is very neat. I think I was debating whether I would say this, but I think I will. I think of all the colleagues and people I've met in the academic world, in certain ways, Andrew has the biggest clarity in his thought process, in the neat versions of his results, and also in the way things are organized in his mind. I think that explains why whenever, wherever you run into him and you mention something, he's immediately ready to tell you a story. Things are structured in his mind in a very elegant way where all the clutter is removed and just the very elegant structures remain. And this has been a big influence in my thinking as well. Okay, then a result that connects more with what I want to talk about today is a result in 2000 by Neil O'Connell, who gave a very beautiful elementary proof of the Hewitt-Savage 0-1 law using this information-theoretic inequality. This is very natural. It says that the information in a random variable z, the total amount of information in it, is at least as much as the information it shares with each one of the different independent random variables xi. So this is for arbitrary discrete random variables z and xi. And this, the way O'Connell uses this is to invoke a manifestation of the principle of measure concentration, which says that sort of geometrically, if something depends in a uniform way on a lot of independent things equally, then it's got to be almost constant. You can't really depend to the same degree on a bunch of different independent things and have great variation. So this is a very cute observation, and it, in a very surprising way, brings mutual information into the study of a result that has to do with exchangeability, which is the topic of this talk. Here's another cute result. So you have the CLT, you have Markov chain convergence. There's, by the way, a lot of stuff has happened since then. I'll mention some of it in the end at the bottom of this slide, but I wanted to give a complete proof of at least one thing. This is an argument that goes back to work by Peter Harmus and Ollie Johnson and myself, but I think this argument goes back to an idea of Peter's. It says that you can get, in a sense, optimal Poisson approximation bounds if you think information theoretically almost for free. So here we're looking at the relative entropy between two distributions. This is the sum of n independent Bernoulli random variables, xi, with, let's say, parameters pi. And we're comparing that with the Poisson law with parameter lambda, where lambda is the sum of the pi's. So another way to write that is as the relative entropy between the law of the sum of the Bernoullis and the law of the sum of independent Poissons that have the same parameters as the Bernoullis. Right? This is just the infinite divisibility property of the Poisson law. And then the data processing property of relative entropy says that this relative entropy is no greater than the relative entropy between the joint distributions of the Bernoullis and the joint distribution of the Poissons. Right? This is the sum is the same function of the x's and of the z's. And then, because these are product distributions, the x's are independent, the z's are independent, this is just the sum of these marginal relative entropies. And each one of these, the relative entropy between a Bernoulli and a Poisson is just the sum of two terms. You don't have to worry about the whole series because you're just summing over what's non-zero in the first argument. And that's something very easy to bound. And it's just pi squared. So in particular, if you look at a triangular array, you do have convergence to the Poisson if and only if this sum goes to zero. And this is the if and only if basic result that you have in probability. And if you want to teach this, I mean, this seems simpler and definitely more elegant than Stirling's formula and the stuff we use. And all it really needs is Jensen's inequality. We just, the data processing for relative entropy is just Jensen's inequality for x log x. Right? So when I wrote out this slide, I'll admit that was yesterday, it reminded me of a meme that I'd seen on Twitter, which is this. Okay. So I want to say two things about this. First, this is not true. Okay? Yeah, that's right. The second thing I want to say is that it is true, and we're proud of this. In that, I mean, there's a sense, a very satisfying sense in a lot of these problems and a lot of these works, and as I said, Andrew has been a champion of this, yes?
Yeah, maybe though you can think of Jensen's inequality as a consequence of the chain rule of information.
Oh my God. Oh my God.
At least if it's the log function.
There's no end to this. Okay. All right. So A, this is not true, and B, it is true, and to the extent that it is true, we're proud of the fact that we can get so much for so little. And getting a lot for a little is, the basic tenet of all science. You want to simplify things, and when you simplify proofs, you really get down to the reason why things are true. So this is exciting. Then a more recent result than Andrew's 86 result on the CLT with Mokshi Maniman, who's also here, I think. Yeah, he's right there in the back. They proved not only that the laws of the standardized sums of IID random variables converge to the standard normal in relative entropy, but that this convergence is monotonic. We now have several proofs of this result using different tools and techniques, but the paper by Andrew and Mokshi is the one that ties in most organically with our general understanding of the entropy power inequality and De Bruyn's identity and the way we connect these ideas. Despite the fact that they're deeply probabilistic, they very nicely and fundamentally connect with our statistical understanding as well. There's a lot of L2 theory there that's at the basis of all of this. So this invites a very appealing analogy with the second law of thermodynamics. It says that the entropy increases. The entropy of the standardized sums increases to the maximum entropy it could possibly have, and that's the entropy of the Gaussian when you restrict the variance of these random variables. And this monotonic increase of the entropy is equivalent to the monotonic decrease of the relative entropy, which is equivalent to this relative entropy ever being finite. This is really as elegant as it gets, and it's a very exciting result. It sparked a lot of connections across the board, and there are many, many information-theoretic approaches that play a crucial role, not just in reinterpreting results like we do here, but also in leading the way in our understanding of probabilistic results, for example, for diffusions and manifolds and for random matrix theory and so on. All right, so now a little bit about De Finetti's theorem. De Finetti's theorem is, again, I tried to not say the word philosophy here because it sounds pretentious, but it's a mathematical result that's an intellectual cornerstone of our understanding of objective probability and Bayesian statistics and so on. And it's in its most basic form, it says that, okay, if you're a statistician, you want to make some assumptions about the real world, and like in any kind of applied science, there's a we don't talk about it, but there's always a step of natural philosophy of how you relate your mathematics to what's happening. And independence is one of the ugliest things, right? I mean, you can't really argue that what mathematically we define as independence very well corresponds to what physically happens. But exchangeability is something that's much more tangible and reasonable. If I get a bunch of samples in some order and I wasn't thinking about the order in which I collected them, then I naturally would describe them as exchangeable because the order played no role in how I collected the samples. And once, let's say I collect a bunch of, let's say I collect infinitely many so that the theorem holds. I get infinitely many binary samples. And they're exchangeable, meaning that any permutation of any finite number of them doesn't change the distribution of the whole thing. Then it turns out that I'm forced to think of the distribution of this binary process as a mixture of IID distributions. So the nature of the problem itself forces kind of a Bayesian thinking on what you're doing. So there is a unique probability distribution on the interval 0, 1, corresponding to the parameters of the Bernoulli, so that my samples are in fact distributed as if I had randomly picked, or someone had randomly picked a parameter p according to this distribution and then generated IIDP samples. And this is inescapable. So this is a very powerful result, both mathematically and intellectually. As I said, it plays an important role, not just in quantum information, in fact, in quantum mechanics in general these days, and also in modern applications of statistics and machine learning and so on. The problem is that it doesn't work for finite state spaces. So finite sequences. You have to have an infinite process, infinite length process. If you have a finite sequence, it can be exchangeable, meaning that you can permute random variables, but it's not necessarily a mixture of IIDs. The good news is that, of course, it extends to general state spaces. There's nothing special about the binary nature of this. But there's a saving grace when something works asymptotically but doesn't work for finite n. You can often hope that it holds approximately for finite n, and that this approximation gets better with large n. So here's a theorem by Diaconis and Friedman. And more interesting than the theorem is their proof. So well, actually, I don't mind not saying so much about my own results. This is fun stuff. So they say the following. Suppose that we have an exchangeable random vector of length n, x1 through xn, taking values in an alphabet of size m. Right? So, and let's say now that among these n random variables, we just look at the first k, small number of them. The distribution of the first k, x1k is just x1 through xk. The distribution of xk, x1k, conditional on their empirical distribution is the same as sampling without replacement. Why? Because if I give you the empirical distribution of the whole n, I give you the counts, how many times each letter appeared, and then every string of length n with these counts is equally likely, right, by exchangeability. Therefore, looking at the first k of them, I'm just drawing k balls out of this urn that has the composition given to me by this empirical distribution, and I'm recording the outcome, right? So if I condition on the empirical distribution and then average over all possible empirical distributions, then I get the distribution under the exchangeable measure of the first k random variables in a exchangeable sequence of length n, and each one of the terms in this integral corresponds to sampling without replacement. Whereas a mixture of IIDs, if I did the same thing and just replaced this by, again, the same mixture, I'm integrating over the law of the empirical distribution of the strings. If I now look at the IID version of sampling, I'm just sampling with replacement according to the conditional distribution. So they said, okay, so fundamentally this problem of comparing the law of the exchangeable string with a mixture of IIDs boils down to comparing sampling with and without replacement. This is vintage Percy, this kind of thinking. And once you realize this, then they sit down and calculate, and they find that indeed the relative entropy distance between the law of the first k random variables in a sequence of length n, which is exchangeable, is no further from a mixture of IIDs in the total variation distance. This is the total variation norm by this amount. A is the size of the state space. K is the small bit that we're looking at, and n is the length of the whole vector. So this is very clean and very nice and very satisfying. And a little over 20 years ago, I had the following heuristic thought in my head, that here's how one might think about going about proving the Finetti theorem. So this is a proof of the infinite version, the classical version. If I have a whole exchangeable process, the fact that it's exchangeable implies that it's stationary. If it's stationary, the empirical distribution, the empirical measure, has to converge by the ergodic theorem. But it's not necessarily ergodic. In fact, it's typically not ergodic, so it will converge to something random. So I know that the empirical distribution converges to a random probability distribution on my state space A. Now, instead of looking at my exchangeable x's, let me look at the simplest possible process I can think of, IID uniforms on this finite state space. Then, if I condition on the empirical distribution, IID uniforms are, of course, I mean, the conditional distribution of anything IID given the empirical distribution of the sample is uniform over all the class of all strings that have that composition. And the same thing holds, of course, for my original exchangeable sequence. But now I know from statistical mechanics that if I condition on the average energy of a system that has many dimensions, and I look at only a few of them, then those few, for a large system, look like their IID with respect to the maximum entropy measure, the maximum entropy Gibbs measure. So in fact, we know from probability that indeed, for the IID random variables, this joint distribution, conditional on the empirical, converges to the product of what the empirical converges to, because now I'm not maximizing entropy because I'm conditioning on something very thin. And then I'm just integrating and I get the result. I don't know if this made sense to you. That was the heuristic I had in mind. And then I thought that, okay, then one can do this and prove the Finetti, and one can, in fact, use the method of types to keep track of the errors in each one of these steps and get a finite Finetti theorem. And it turns out that I mentioned this to Lambros 20 years later, and we actually were able to complete this proof rather simply and get this fun but poor bound. It says that for any finite exchangeable sequence, the law of the first k symbols of the n string that you start with is close in relative entropy to a mixture of IIDs by to this amount. And this is not a very good bound. This is pretty slow convergence. It's definitely much slower than what Diaconis and Friedman tell us is the right rate. So if you apply Pinsker's inequality to this, you get this kind of bound. This is just bad. And it's definitely not as good as k over n. So how much time do I have? Okay, keep going. Okay. All right. Then we thought we might, so I'm lying, really. This was the second paper we wrote, because 5 minutes, okay. I'll tell you the story. I told Lambros of this idea, and he completely ignored this. He said, this is very interesting. And the only thing he kept was the words information-theoretic and Finetti, and he came up with a different proof. And then after we published that, I said, remember I had this idea, you think it's really junk? Did you just ignore it for a reason? He said, oh, no, I forgot. Okay, we'll make that work as well. Okay, so this is actually the first thing that we wrote, but it made more sense in telling the story to mention second. This is special to the case where we're looking at binary sequences. It's a slightly better bound with a completely different information-theoretic proof. The information-theoretic proof is based on this bound that comes from a direct calculation that has a nice interpretation. It says that once you condition on the empirical distribution of your sample, then there can't be very much information that the first k-1 symbols tell you about the kth one, and there's a quantitative bound, and then you combine that with our earlier thinking, and you get this theorem. It's better than before, but still it's far from k over n. So if you combine with Pinsker, you get this total variation bound. Not great. Okay, so then we were joined by Mario Berta, who had some ideas that originate from quantum Definetti theorems, and we were able to prove this improved bound for, in fact, this is for random variables in any discrete set, finite or countably infinite. The relative entropy between the first k symbols in a string of length n, which is exchangeable, and a mixture of IIDs is no larger than this. So this is getting closer to what we want. It's also more general, and the proof is really satisfying because you really are doing soft things in a very clever way. And it's not elementary in the sense that we prove this for general abstract standard spaces, but the argument is in fact a soft argument. And extends to general state spaces, as I said. But there's a weird thing, which is that now the mixing measure here, in the mixture of IIDs, is not the right one, or is not the one that we believe is the right one, or at least is not one that anyone has ever used before. It's something that just works technically, and it gives us this bound, which is getting closer to what we want, to k over n. I won't say anything about the proof except to say that it's based on this reinterpretation of the chain rule for mutual information. Again, it's a mutual information bound that gives the result. And it's this one and some smart ideas that Mario brought to us on how to handle these things. Okay, and then, so finally, okay, so now this is kind of surprising and a little weird. There are 3 different information-theoretic proofs of finite Definetti theorems, and this reminded me of a paper by Percy Diaconis that has a similar title. It's called 10 Definetti-style theorems in search of a theory. So now we have 4 information-theoretic Definetti-style theorems. I don't think they're in search of a theory. In fact, I think that in this case, what's exciting is the opposite thinking, the fact that there's generally information-theoretic thinking that gives you strong results with very elegant and appealing proofs, and the different proofs are different. We don't have a sense that there's some underlying unifying truth and beauty that we're missing. There are just 3 different information-theoretic arguments that work. Okay, so then we were joined by Oliver Johnson, and we went back to the idea of Diaconis and Friedman, which was to compare sampling with and without replacement. And in particular, Ollie took the lead in that project, and he proved some very nice and strong state-of-the-art bounds for the relative entropy between these 2 distributions that are very valuable and very useful in applications that have to do with sampling. But it turns out that for our purposes, we only needed something that Stam had done a while back that we weren't aware of. We figured out halfway through writing the paper. So combining this thinking with Stam's bounds, we were able to get a finite Definetti theorem in relative entropy, which is stronger than anything that existed before, with the right rate. This is k squared over n squared, and if you combine with Pinsker, you get the right thing.
Am I right that even the dependence on the size of A is now better? Because when you take...
It isn't, because we had here the entropy, this could be log A. So it's worse. But the dependence on the alphabet size is critical for some applications of this to approximation theory and in quantum mechanics, and that's something we're trying to figure out.
But compared to Percy's?
Yes, compared to Percy's, it's better. Yeah. Thank you. Yes, well spotted. Right, so that's all I had to say. There's a lot of successes in this story that's been going on for 60, 70 years now. There's still lots of fun to be had if you're interested. Andrew has been one of the people with the most, I don't want to say rigid, but most clear bearings in his scientific compass, and he's been one of the people leading and inspiring the field. And this area is this niche area that I talked about is still actually active, and there's applications and fun stuff to do there as well. So I'll stop here.
Questions or comments?
Is there anything similar known about finite exchangeable arrays?
No. Well, not information theoretically. I mean, there's the work of Aldous.
But that's the infinite case.
Yeah, there are results that present finite end versions of Aldous's finite exchangeable arrays, but I haven't seen any information theoretic arguments. Did you have an answer to that question? Oh, okay.
Peter?
So, you mentioned that Ioannis said that there should be some kind of theory. Stephen Lauritsen kind of made an abstract theory which also included the conditional limit theorem in a framework like this year. So I think definitely we should.
Yeah, there is an understanding that all of this has to do with projections of weird spheres. Yeah, I mean, that intuition has been around, right? It goes back to Boltzmann, I think. But yeah. By the way, Gibbs lived his whole life here, didn't he? It's very appropriate that we're talking about Gibbs.
He was extremely important here in the Sheffield Scientific School. But whether he was his dad was a priest here. His statue in the cemetery over there is bigger.
He lived his whole life in New Haven, except for 2.5 years he lived in Germany, and he lived in the same house where he was born his whole life.
Wow.
Yeah.
You have a, no, okay. You do? You're raising your hand, okay. A thought. So the importance of the exchangeability in the Bayesian justification is in saying, see, there's got to be a prior, so you can write it as an IID model with a prior. More generally, if you have Markov processes that are ergodic, or even general stationary processes, you could be asking, can I write that as a Bayes mixture of ergodic processes? And the ergodic decomposition theorem of Oxtoby and others does that.
Yep.
Are there corresponding questions about how close the finite sample stationary processes are to mixtures of ergodic processes? And have you thought about that?
There is, I mean, for the Markov case, there is a Markov representation theorem, and Percy, again, I think with Friedman and maybe someone else, they have a paper on finite versions of that. In the generally ergodic case, one would be worried and tempted to conjecture that there wouldn't be rates.
There wouldn't be rates.
Yeah, and we have Andrew here, who's
good at showing how slow things can be.
yeah. How you want to be known.
All right. Anything else? Good. Thank you very
Right.
much.
Thank
Let's
you very
thank you
much.
again.
Thank you.